Hey guys, today we're going to talk about secant segments. So a secant segment we define as a segment of a secant that has exactly one endpoint on a circle. So for example, AC, that's a segment of the secant of this line over here, and it has exactly one endpoint on the circle. So AC would be an example of a secant segment. Also, we have like AB would be another example. AB would be a secant segment. It has our endpoint right here on the circle. We also would have AE. That would be another secant segment from A to E, and AD. So you just have to be a segment of a secant, and one of your endpoints, exactly one of them, has to fall on the circle. Now we also have like a subgroup of these. That would be like these two here. These are called external secant segments. And the way we have it, or the way we can tell if it's an external secant segment, well, that's because AB, like that segment, is outside of the circle, and AD is outside of the circle. We still have one endpoint on the circle, but we're going to be outside, where the other two, they go through the circle. So these would be external secant segments. And well, that'll be important with some of the theorems we talk about today. So the first theorem that we talk about, and we're on page 752, this theorem states, if two secants intersect in the exterior of a circle, then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant segment and its external secant segment. So what this is saying, you have two secants right here. If they intersect outside the circle, they do at point A, then the product of the secant segment, so like AC, the product of AC, and its external, AB, the product of those two is equal to, well, the product of AE, the secant segment down here, and the external segment on that secant, which would be AD. So this is the relationship that exists here. Secant segment AC and the external secant segment AB, and then the secant segment AE and its external secant segment AD. The product of those is going to be equal. And we can show how this relationship exists. We'll just rewrite it over here. Again, it was AC times AB is going to be equal to AE times AD. And to do this, you would need to draw a few little lines in here. You could draw in segment DC, segment BE, and then we're going to try to use similar triangles to set up a nice ratio and isolate. So here, one of the things we want to notice, we're going to look for some congruent angles. And right off the bat, I know we're going to be using this angle, so I'm going to say angle A. Talking about this angle right in here. Angle A was obviously congruent to itself. Or if we want to be more specific, we could say angle like BAD is congruent to angle DAB. This angle right here is congruent to itself. That's our reflexive property. But in order to use some similar triangles, we need to have at least two pairs of congruent angles. So let's look at some other angles here. And the other angles that we could tell that are congruent, well, another one would be like angle ACD. Angle ACD, this angle right here, that is actually congruent with angle AEB. And the reason why these two angles are congruent is if you look, and now I'm going to kind of bold these, angle AEB, well, that angle is an inscribed angle, and it intersects our arc DB. And then ACD, that angle is also an inscribed angle, and it intersects the same arc. So if two angles both intercept the same arc, and they're both inscribed angles, and they're congruent to each other, then through this right here, well, we have triangle ACD is going to be similar to triangle AEB, and that is because we have an angle-angle or we have angle-angle similarity here. So we know these two triangles are similar to one another. These angles correspond, this angle corresponds with itself, and we don't need the third angle here. But since we have similar triangles, we can use the similarity statement, and from that, we can make some nice relationships here. So I'm going to write it as AB over AD. That ratio should be equal to AE over AC. That's the ratio that exists here. And then by simplifying the cross products, AB times AC, I'm going to write that as AC times AB, is equal to, well, AE you'd multiply with your AD. And that right there is what the theorem says. So those products of your secant segment and your external secant segment is going to be equal there for both of your secants. All right, on to our second theorem of the day, and then you can get into applying some of these. So our second theorem, let's see, we have a nice circle here. That first theorem was talking about two secants. Now our second theorem is going to talk about what happens when you have a secant, like this one right here. We'll use the exact example in the book. A secant that intersects with a tangent outside of a circle. So this theorem states if a tangent and a secant intersect in the exterior of a circle, like they do here, J, then the square of the measure of the tangent, so the measure from the point of tangency to the point of intersection, that's JK here, the square of that, so JK squared, is going to be equal to the product of the secant segment and the external secant segment. So JM times your JL, external segment and the segment, times JM. That's going to be the relationship that exists here. And we'll show a little proof of this one. So this is what we're going to try to show. And we can do that. Well, let's see what we can create. In order to do this, we would need to draw a couple little segments in like this. And then I'm going to look at some relationships. So one relationship that we can look at, we're going to try and set up some nice angles here. Let's color code. If we look at angle, let's do JKL. Angle JKL. So angle JKL, and that's with our tangent here intersecting. Notice that we intercept our arc LK, and we should know from a past theorem that we talked about that this is going to be half the measure of that arc LK. JKL is going to be half the measure of the arc LK. And we also can look at angle KML. Because KML, that intercepts this arc, and the relationship of an inscribed angle that intercepts an arc is it's half the measure of that arc. So these two angles are both half the measure of that arc, which, really nicely, we should be able to figure out that means those two angles are congruent to one another. So angle JKL is congruent to angle KML. And that is simply because they both are going to be half the measure of this arc. So they're going to have a relationship that they're congruent with one another. It turns out to show this relationship is true, we're also going to use angle J. So angle J is congruent to itself through our reflexive property. And then now we have two angles that are congruent. So from these two, we should have angle-angle similarity somewhere. So let's match up what we have angle-angle similarity with. So triangle, we'll triangle JMK. JMK is going to be similar with, well, it's going to be triangle, JKL. So triangle JKL. Your J's are obviously going to correspond with one another. And then your your K is going to end up corresponding with your M because of those angles that would have been congruent to one another, right here and right here. So those angles would be corresponding with each other. So similar triangles are a little tougher to see in this one, but these are your two similar triangles, and that's through angle-angle similarity. And then from there, you can go ahead and make a little ratio of your corresponding sides. So JK to JM, JK to JM, use that similarity statement, is going to be equal to the ratio of JL to JK. JL to JK. And this relationship is true because in your similar triangles, the ratios of corresponding sides will be equal to one another. And then you can simply take cross products. JK times JK equals JL times JM. JK times itself, well, that's JK squared. So this relationship right here, well, that's what we were trying to show. So simply by having two similar triangles, a little tougher to see here, your triangles JMK and JKL. Since those triangles are similar to one another, then you can make this little relationship and get to our final conclusion. All right, so go ahead and now take these two theorems and see if you can apply them. Key thing is knowing the relationship, but it's nice to know where the theorem comes from.